This is the last topic in the rotational series, and it's on momentum, but angular momentum. So the case that has been made all through this series is that linear dynamics, linear kinematics is very similar to rotational kinematics and dynamics. And the same can be said of momentum. Recall that linear momentum is mass times velocity. So if I want to define an angular velocity, I'd probably just use the variables that are analogous to mass and velocity. And those are moment of inertia and angular velocity. So that's my angular momentum. And I will try and make some relationships with torque and time. So I'll start with my relationship, which is analogous to, remember, F net equals ma, where this sum of the torques is F net. I is m, and alpha angular acceleration is a. And I will expand on angular acceleration to get change in omega over time. And if I expand, or if I distribute rather the I to the omega final and the omega initial, I can call this term to be my change in L, my change in angular momentum. So final minus initial is my change in angular momentum. So the relationship I have then is the sum of all the torques is equal to the change in angular momentum over the time that the torque is being applied. And this looks very similar to the impulse equation. Remember, the force, or the sum of all the forces acting, is equal to the change in momentum over time. Then we took that and we said, if we define the system correctly, say two masses are heading towards each other, m1 and m2, and we call the system both of those things together, we could say there's no external force, so there's no change in momentum. We're going to make the same argument here. If we define the system correctly, then the sum of all the torques is 0. So the change in angular momentum must be 0, which means that angular momentum, like linear momentum, is conserved. So Li equals Lf for the right system, right meaning the defined system where there's no external torque. So two examples here to prove this. We'll look at a figure skater and neutron stars. So here's my figure skater. They're on ice and they have their hands extended and they're making some twirl. So they have an angular velocity omega initial. Now if in that same twirl they pull their hands in, there's no torque happening on them. There's no external force. So the initial angular momentum must be the final angular momentum. So what's different about these two cases? Well, I would expect that the moment of inertia here would be greater than the moment of inertia of the skater here, because you have more mass extended further away from the axis of rotation being right down the middle of that figure skater. So I initial is greater than IF. And if I write this expression and expand it for I in omega, I could come up with this. And if I'm saying that the I final would be smaller than the I initial, then I would have to expect that omega final is greater than the omega initial. And that's what we see if we ever have seen figure skaters. So they'll come from this position and they'll bring their hands in, and by doing so, they increase their angular velocity. Here I just put in some numbers if that's easier for you. Maybe this will make sense better. So let's say that my I final is half the value of my initial I. So I plug that in, 1/2 I initial, and I'm trying to figure out, well, what value of x is omega final to an omega initial. So I put that in, and I cancel out my terms. Omega initial cancels out, I initial cancels out, so I'm left with 1 on this side. Remember, that's not 0, even though I canceled out these two terms. 1 is equal to 1/2 x, so x must be 2. So the speed the angular speed of the final case must be twice as much as the initial case. The neutron star is what's left over after a star goes supernova, which is when the star explodes out its guts. You are left with some mass that condenses in on itself. So the reason why it's called a neutron star is because this tightly packed mass has some some electrons and some protons, and they get closer and closer to one another, more tightly packed. There's the pressure is increasing. The speed at which these particles are traveling increases. So when they smash into each other, they become a neutron. So you've got this big mass, and it is all collapsing, which means that the moment of inertia, is going down. Now there's no net external torque on the neutron star, so if the moment of inertia decreases, the angular velocity must increase. And that's what we see with the neutron stars. Its rotation increases as it continues to collapse in on itself. Hope that made sense. I will see you guys soon.